Welcome to Calculus. Today we will investigate interpretation of the derivative as an instantaneous rate of change, focusing on applying the derivative definition to yield a rate of change function with connections to a real-world scenario. We'll take a look at two scenarios, one a simple to begin and then a second more complex. So our first scenario here involves the volume V in cubic feet of a balloon, and it is expanding according to the function v. Again, volume equals v as a function of time, v of t, equals 4t. So notice that the function itself for volume here is linear, where t is time in seconds. What we're trying to answer is this question: at what rate is the volume changing with respect to time? And then we want to indicate what are the units of this rate of change, which we're again interpreting as the derivative of the volume function. So we'll begin by remembering how we define the derivative. So we'll write that first here. The derivative of the volume function, in this case, according to time, by definition is the limit as h approaches 0 of this difference quotient. So the way that we'll write this is v at t plus h minus the original v of t, all divided by h. And again, that's just our basic definition of the derivative as basically algebraically the slope of the tangent line at any point on that original volume function's curve. Well, let's apply that to this specific situation involving volume of a balloon as it's expanding. So just to get our pieces in place, let's define first of all v of t plus h. We'll define these two parts that are in our numerator of the difference quotient. So v of t plus h is going to be the original function v of t, which is 4t, and what I'll substitute in is t plus h. And we can distribute that 4 here at this step, so that'll be equal to 4t plus 4h. The original function v of t we see is just 4t. And with those two items defined, now we can substitute into our definition. So what we'll calculate here, and I'll just continue this to the right, is the limit as h approaches 0. In my numerator, I'm going to place those two substitutions. So we found that v of t plus h was in parentheses 4t plus 4h. We're going to subtract there v of t, the original, which is simply 4t. And that's all divided by h. So again, I took my original definition, substituted in the v of t plus h and the v of t according to my specific function. And now I want to simplify that setup. So again, where we normally look is here in the numerator. So in terms of simplification, I'll start by removing those parentheses. And I'm looking for a cancellation. So I definitely see one here in my t terms. So 4t minus 4t would cancel. That's a 0 pair. And my next limit statement would be the limit as h approaches 0 of 4h over h. So I do want to try direct substitution, but before I go there, I notice that I have an h over h. Again, that's another cancellation, and that would yield the limit as h approaches 0 of simply 4. So remember, if I have the limit of a constant function, in this case 4, there's no substitution to make for h since all the h's have canceled out, and that function is simply 4. So my final answer here is v prime of t, or the derivative of volume with respect to time, is simply equal to 4. Now we do want to say what the units will be. So again, if the original expression is defining volume in cubic feet, the rate of the change of the volume will be cubic feet per the time unit, which in this case is seconds. And that we will box. Let's take a look at a second real-world scenario that involves a more complicated function. So just to note again, this first example was a linear function. So algebraically pretty straightforward. Let's take a look at a scenario where we've got a cubic function, which again is a more traditional description of volume since there's 3 dimensions to volume. So here we're considering the volume V of a sphere of radius r, and that's this function V equals 4 pi r cubed over 3. That famous volume formula for a sphere that we attribute to Archimedes. If the radius changes from r to r plus delta r, find the A, change in volume, B, average rate of change of volume with respect to radius, and C, rate of change of volume with respect to radius. So we see that it looks like we've got a totally different question here, but really what we're seeing is the same question we saw in the first example, but with the parts kind of spelled out in part A, part B, part C. So we'll focus first on change in volume. So we just need to think about what's happening to this sphere. So its volume, if it's going from a radius of r to a volume of radius plus a change in r, again, delta is the Greek letter that we assign to the parameter of change. That means that this volume is increasing, the radius is getting larger. So the way that I would express the change in the volume would be V at the larger radius, so that's radius plus delta r, minus the original volume at the smaller radius of simply r. Now we need to keep in mind that that really is the numerator in the definition that we had for the derivative. So just again, to bring that back so that it's in view, really we're looking at the derivative of V according to the radius. So by our definition, that's the limit as h approaches 0 of V of r plus h minus V of r over h. So what we're calculating in part A is really this numerator. And what we'll do in part B and part C is include then the denominator h, and then we'll take the limit in part C. Now, one thing that I'd like to do just to simplify our notation, delta r is going to be a lot to write, and it's going to be tricky to keep that in mind that that's one variable. It's not 2 variables multiplied, it's 1. So I'm going to make a substitution here. I'm going to call delta r h. And again, that's just to reduce the clutter in our notation. So now I'm ready to set up this difference. Again, that's the numerator from the definition. So let's define our 2 pieces here. So volume of r plus h, so it's the larger volume after the radius is increased by a distance of h, is going to be that original function, so 4 pi over 3 times r plus h cubed. And notice how I've just pulled that radius over to the side, and I've grouped my 3 constants as a fraction over on the left, 4 pi over 3. At this stage, I want to expand that and finish that algebra here. So my next step is going to be to expand r plus h and to show those 3 binomials. So this is 4 pi over 3 times r plus h thrice. So I'll expand it so we can see it. Now I want to distribute all that out and have just a simple polynomial. So now what I've got is 4 pi over 3. I'll leave that first r plus h and multiply through the second 2. So this is a double distribution or a FOIL. So first term r times r is r squared. Outer terms r times h is going to be hr. Same as my inner terms, hr, so I've got 2 of those, plus 2hr. And then my last term's h times h plus h squared. Now I want to distribute r through that trinomial and then h through the trinomial. So this will be 4 pi over 3. And then I'm going to distribute the r. So I should draw where I'm distributing it. So to each of those 3 terms. So first what I've got is r times r squared. So that's r cubed. Secondly, r times 2hr, that's 2hr squared. Thirdly, r times h squared, so that's plus 1rh squared. Now I'm going to focus on the second distribution from h. Again, multiplying times each of those same 3. And to help with the combining of like terms, I'm going to stack these products according to what they'll combine with. So h times r squared is 1hr squared. So notice I'm stacking the like terms there. Secondly, h times 2hr is 2rh squared. And last, h times h squared is h cubed. So that is a singleton there since it's the only occurrence of h cubed. So now I'm ready to add this all up. So this is 4 pi over 3 times r cubed plus 3hr squared. And I'm going to reverse r and h squared here since h squared really is a constant. So that's 1rh squared plus 2rh squared, that's 3. And again, I'll call that h squared r. And lastly, plus h cubed. And at that point, that is a polynomial version of the original cube. Well, let's also define our second one. So the original v at r is simply 4 pi over 3 times r cubed. Now, what we need to do is bring in these 2 pieces and substitute them into this change of volume, which is our numerator in our definition of the derivative. So I'm going to take these 2 pieces and write their difference. So we'll do that up here. And we need to show what's substituting where. So for this first term, the v at r plus delta r, which we're calling h, is going to be this polynomial we just calculated. I'll circle it there in red. So this is going to be 4 pi over 3 r cubed plus 3hr squared plus 3h squared r plus h cubed. And then I'm subtracting from that the original v at r, which again is 4 pi over 3 r cubed. So that is the difference. That's the change in volume. To help myself out with the next step, I do want to simplify that. So I do notice that I've got a common factor there, 4 pi over 3. So I'll factor that out. Just drawing a separated line there. So 4 pi over 3. And then let's write what's left. So from the red side there, it's r cubed plus 3hr squared plus 3h squared r plus h cubed. And then from the blue group, minus r cubed. Now, once I do that factorization of 4/3 pi, I see that I have a cancellation. R cubed minus R cubed cancels. So my final expression here for the change in volume is 4 pi over 3 times 3HR squared plus 3H squared R plus H cubed. And I'm going to box that. That is the change in volume, which again corresponds to my numerator in the definition of the derivative. At this time, we want to then proceed to part B. And what part B is asking is, what's the average rate of change of volume with respect to radius? So again, we're connecting this to the definition. We'll write it again so we have it in view. The limit as h approaches 0 of v of t plus h minus v of t over h. So what we just calculated, again, just to connect it, is the numerator. That's the change in volume. And that's where we'll substitute that expression in green. The average rate of change would simply be if I took and divided by h. So notice we're building our difference quotient here piece by piece. So really for this part, what I'm going to incorporate is the numerator and the denominator. What I won't incorporate yet is the limit. So at this time, let's set up our fraction. And again, what I'll substitute in for my difference in my numerator is this 4 pi over 3 times that polynomial 3h r squared plus 3h squared r plus h cubed, all divided by h. So to find the average rate of change, we just incorporate that divisor of h. And I see automatically that I've got some cancellations because each of my terms above within that parentheses group includes a factor of h. So I'm going to cancel the one below and one each here. So h cancels, h squared leaves just h, and then h cubed leaves h squared. So my rate of change, average rate of change here, is going to simplify down to 4 pi over 3 times 3r squared plus 3hr plus h squared. So again, I'll box that. It's again an intermediate step in calculating the derivative according to this definition. So you can kind of anticipate the only component left from the definition of the derivative is the limit as h approaches 0. So in part C, when we're asked to find what's the rate of change of volume with respect to radius, really what we're looking at there is what's the instantaneous rate of change. And remember, the instantaneous rate of change is that average rate of change, but incorporating the limit. So all we've got to do is take and say now, okay, I'm going to calculate the limit as h approaches 0 for this simplified fraction, because now what we've got is this entire difference quotient simplified down. So that is going to be for us 4 pi over 3 times, in parentheses, 3r squared plus 3hr plus h squared. And since it's all simplified at this time, all I need to do is direct substitution. So I'm going to drop that limit notation. We got 4 pi over 3. And I'm not doing anything when I see r. Really what I'm substituting for is 0 for h. So r squared. So the second term does have an h factor. So we'll substitute in a 0 there. Times r plus, and then the last term is h squared, and we'll substitute that in as well. So when I go to evaluate here, I've got a cancellation of these two latter terms. Zero involved in a product is going to make those terms zero. So what this reduces down to is 4/3 pi times 3r squared. And then what I see is my 3 divided by 3 is going to cancel. And what we're left with is a much simpler function, 4 pi r squared. Four pi r squared. And that we want to box because that really is the function that we could represent the instantaneous rate of change of volume with respect to radius. And just to remember, that is the derivative of the original volume function with respect to the radius. Thank you for joining for this investigation of interpreting the derivative as an instantaneous rate of change in real-world scenarios. I'm going to let you go and interpret your own real-world scenarios in terms of the definition. Thank you for joining. See you soon.